Hello everybody, this is the second lecture on a series of lectures on Introduction to Radars. Today we are going to learn about modulated CW radar, and CW stands for continuous wave radar. Okay. So in the last class we classified radars into monostatic and bistatic. In monostatic you had a single antenna and a transmitter receiver antenna in a single location where you transmitted a pulse which would go and hit the target, and it would be received back at the same location, okay, by a same antenna, or it could be a different antenna. So this is known as a monostatic radar, while the other kind of radars is known as bistatic radar. So in one location you have a transmitter, so that will illuminate the target with an RF pulse, and the reflected pulse would be collected by or received by another antenna located at a different location. Okay, so this is known as bistatic radar. And then we went ahead and we derived the radar range equation. That range is the distance. If you draw a direct line between the radar and the target, whatever is the distance obtained, that would be known as range. Okay, and we derived this equation in the last class, where the range is given by this equation, where PT stands for the power transmitted by the radar. That means more the power you transmit, the range is going to be more. G stands for the gain of the directivity of the antenna. Obviously if you have a directional antenna, then the range will be high. So all these are the terms which is controllable for maximizing the range. Okay. And then this sigma, that was the radar cross section of the target. Okay, so that is not controllable by us. So whatever is the target, okay, so whatever metallic area it offers for reflection of the RF signals, okay, so that is known as the radar cross section. So that is not a design variable available with the radar designer. And then we have the antenna effective area. Okay, that is again a variable, design variable available. So larger antenna will capture more signal, received signal, so that would help us in increasing the range. And S minimum is the minimum detectable signal by the radar amplifier, right? So you can minimize this, okay, so and maximize the range. Okay, then we also saw we can't minimize this to an level below something known as threshold level, right? So if you see, there will always be some noise. Noise is nothing or the RF signal being reflected by the by ground clutter and things like that. So there will be some noise always available. So unless we set a threshold, okay, then this noise cannot be eliminated. So you have to set a threshold where only the actual pulse which is reflected from an target, that signal should be above the threshold level. So you have to judiciously set the threshold level. So if you set the threshold levels here, so all this noise which will be picked up by the antenna, they will all trigger and show it as targets, and then your scope will be cluttered with noise, like false alarm you can call this. So you have to set the threshold here. So that we learnt in the last class, right? And then we also saw that the PRF is nothing but the pulse repetition frequency. So now you have one pulse being transmitted here, it is received here. Again the second pulse being transmitted, it is receiving here. But if you have a target which is very, very far away, then you have this being transmitted, and then it is being received here. Meanwhile you have transmitted one more pulse here. So now the distance will be computed like this, right? Whereas the actual distance is given this much, right? So that, and hence the PRF also limits the max range. So R max with respect to the PRF will be given by C divided by 2 PRF, okay, where C is the velocity of light, right? Velocity at which the RF pulse moves. So these two things we learnt in the last class, right? Today, before we learn about an CW radar, let's see the classification of radar in terms of its functionality. So radar can be classified as a primary radar or a secondary radar. So what is primary radar? Primary radar means you have a radar which will transmit an RF signal which will go to the target, and it will come back, right? The reflected wave is again captured by. So here you just have to have a passive metallic surface. Okay, so this is known as primary radars, right? So where you are transmitting and receiving, and this is just a passive metallic surface which will reflect the RF pulse. Okay, whereas secondary radars are you have an like mostly this is the primary radar, and you will have a secondary radar antenna on top of that. Okay, here what it does is it sends an interrogation pulse. It goes to the aircraft. In the aircraft you have a transponder. Okay, generally it is known as IFF transponder, identification friend or foe. So that will receive the pulse, and it will send back a reply pulse, and in the reply pulse it would generally say the code of every aircraft will have its own code, so it will send back that code, right, and that will be decoded at the radar. So primary radars cannot distinguish one aircraft from other, right? It will only say, okay, there is a target available at this particular range. Whereas the secondary radar, since it is going to receive the information from the aircraft, it will also be able to see which is the aircraft. So in ATC and all, it is very important, right? You have many civil aircrafts which are coming, so it will give not only it will give an blip on the scope that there is a target there, it will also say the aircraft number also. So that is very useful. So obviously this range can be much higher than the primary, because you don't have to transmit that much amount of power for it to go there and get reflected and come back, right? You just have to send whatever power is being transmitted, that has to just reach the target, and then from the target you have another system or another transponder which is going to reply. So you don't have to cater for the power being sent to go hit the target and getting reflected back. So obviously secondary radars will have a larger range. So this is also very useful in war times, where we have our friendly aircrafts and you have your enemy aircraft. So when we use an IFF in the war scenario, those IFFs will be coded, so that there will be some cryptography involved there. Only our friendly aircrafts will be able to respond correctly. So all those aircrafts which are not responding properly, we know that they are the enemy aircrafts. Okay, so that is how secondary radars work. Now coming back here, so we know what is a primary radar, what is a secondary radar. So again, primary radar can be classified into pulsed radar and CW, continuous wave radar. So in the last class we did that derivation of range for an pulsed radar. Subsequently again pulsed radar, that pulsed radar, whatever we learned last, that could only detect the range. Okay, but again they can be modified into an MTI, that is moving target indicator, which will give the velocity also, or a Doppler radar, which we will see in the subsequent classes. Okay, as of now we have learnt about pulse radar and the radar range equation, which will give just the range. Now again, the other kind of radar which is available under the primary radar is known as CW radar, or continuous wave radar. Okay, here you are not sending pulses, you are continuously transmitting RF signals, so that is why it is known as CW radar. They can be again classified into modulated and unmodulated, right? So we are going to see about modulated modulated radar in this class, and we are going to learn about unmodulated in the next class. Okay, so let's talk about now. So this is what we are under radar, primary radar, and under primary radar we have CW radar. CW radar, under CW we have modulated CW radar. So we are going to learn about that today. So this is how a modulated CW radar frequency looks like in the time domain. So you have a carrier frequency which is continuously changing with respect to the time, right? So I have FC. Look, the transmitted frequency is continuously increasing. It's reaching a peak value. Again the frequency is decreasing. It's coming to a negative peak, again coming back. Okay, so I have a sawtooth waveform, or a triangular waveform being transmitted. A triangular waveform, not in terms of amplitude but in terms of the frequency, right? So this is the center frequency, and the maximum deviation of the frequency is given by delta f. Okay, maximum deviation of the frequency. And also if you see here, this time period, okay, from here to here, right, this triangular this triangular waveform periodicity is given by 1 by Fm. Okay, so Fm is the frequency of the triangular modulating wave. Okay, so this is this frequency at which the main carrier frequency is changing is known as Fm. Now I have an wave, say at t is equal to 0, I have transmitted some signal, this signal, carrier signal, and continuously this with respect to time it is increasing. So my received signal, okay, this particular FC which I have transmitted, it will go to the target and it will come back, and the time taken now for that to travel to the target and come back, received signal, this is indicated as t here. So at this particular time, okay, here the received signal will be FC, whereas by that time my transmitted signal, or the one I have a transmitter, that transmitter frequency has moved on till here, right? So there will be a difference in frequency here. So at any given point of time, like suppose if I take here, this is what I am transmitting and this is what I am receiving. So this is the difference of frequency, which is known as the beat frequency. That is the difference between the frequency being transmitted and frequency being received, right? Now if I take it now, suppose the target, now this is the antenna, and this is a target, so it is going here and coming back, the time is t. Suppose I have a target which is very far away, so it will go there, and it will take more time, right? So in that case, okay, this signal will be like this, right? It will come, no, it will take much more time for this FC to reach back. Instead of this much t, it is going to take this much more time. Now accordingly, the beat frequency which will be generated will be higher. So if you see here, the beat frequency which will be generated is proportional to the range. Okay, so that is the principle of operation of this CW radar, right? So now if you try to write an equation for that, so the rate of change of the radar frequency FC, okay, rate of change will be delta F. So this much is the total frequency change, and from here to here it is only half the time period. Okay, delta F is from peak to peak, right, from here to here, and this time from here to here, okay, this is half of this 1 by Fm, right? So half of 1 by Fm. So this gives you, so delta F divided by half of 1 by Fm will give me the rate of change of Fm. So if I have to find out in this time, okay, in this time, now how much the frequency changes, so I need to multiply it with by t. So I have multiplied it with by t. Now t can be written, this is the range, right? C is the velocity of the excuse me, pulse which is traveling, right, and it is covering 2r distance, right? It is going, hitting the target and coming back. So 2r is equal to c by t, or t I can write it as, right, t I can write it as 2r by c, right? If I substitute that 2r by c out here, right, and this is the beat frequency. Now from these two equations, right, if I have to find out just r, I can write just target range, r is equal to, right, now c f beat frequency into 4 into delta f into fm. So if you see in this equation, c is fixed, okay, delta f and fm is fixed by a design, right? So r is proportional to the beat frequency. So if obviously if the target is at a further distance, then in that case the beat frequency will be okay, more, right? If the target is close, beat frequency will be lesser, and if the target is very far, the beat frequency will be higher. So this is the way the range can be computed in CW radar, modulated CW radar. So this is another graph which I explained there. So there are two targets. Okay, one is very close, and this is the green line which is indicated by the blue, and this target is slightly further away. So obviously the received, it will take for this FC to go and come back, it will take more time, whereas in this case, since the target is close, it will come back here. So if you see here, then the beat frequency here, HF2 will be more than the beat frequency for the target which is closer. So from the target range equation, you can know R is proportional to the beat frequency. So this is the basic principle of operation of an CW radar. Right now, if I beat these two frequencies, or I put these two frequencies in a mixer, so this is the kind of output which I will get. So here, if you see in the crossover range, okay, the beat frequency will be because here this is making an going to the top and coming back here. So here you will have an erroneous beat. So here also you will have an erroneous beat frequency. Here you have the correct frequencies. So if you take then, but this will be for a short duration of period. But if you take an average of the beat frequency, that will be again proportional to your, the average beat frequency will be proportional to your range out here, right? So where are these modulated CW radars used? Generally, if you have an aircraft which is flying over a terrain which doesn't like a hilly terrain, for example, then this altitude, right, from here to here, right, this is varying, right? So so what we have is how is the altitude indicated in aircraft? Ages back, it used to be the pressure altimeter, or known as the barometric altimeter. So the pressure at any given altitude, okay, will be different, right? So the pressure at the mean sea level will be different, and as you keep moving up to from the mean sea level, the pressure drops. So based on that, you can calibrate, and you can based on the pressure which is being sensed, because at higher altitudes you will have lower pressures, right? So based on that pressure, you can have an altitude indication, but obviously that is prone to errors. Okay, you need to have day's pressure, and pressures also can fluctuate. Okay, so that is one way of doing it. But that will give you the altitude from the mean sea level. But when we are flying on a hilly terrain, you are not interested in that, right? You are more interested in the actual height from the ground level, so that there is no collision, right? So this is more important, right, for us. So in that case, we can use an CW radio altimeter. Okay, so you transmit a signal, you receive a signal. With that, and you can compute the range. So you have a radio altimeter. So if you see here, radar, it is written radar here, altitude in feet. So this gives a radio altimeter. Okay, so this altitude, which is displayed in the aircraft, is the actual distance from the ground level, and it uses a CW radar. Similarly, you could have this is an analog indication. You could have a digital indication also, where you have this, right? Altitude AGL, altitude from above ground level. AGL stands for above ground level. MSL stands for altitude from mean sea level. Okay, so from the mean sea level altitude will be obtained by an barometric altitude sensor, whereas above ground level will be obtained from a radio altimeter. Okay, so that is the difference. Now, how to make an hardware out of this concept? So you have you can have an RF VCO. So you have a modulator. So if you see the frequency, right, this modulating frequency is generally of 50 to 30 hertz. Now I think I missed out that ranges. So radio altimeter generally this is the operating frequency. Okay, 4.24 gigahertz. And delta F, okay, that is the bandwidth required, will be 100 to 200 megahertz, and the modulating frequency here, FM, is of the range of 50 to 300 hertz, and generally radio altimeters can the max range permitted where it can give good results is 1 to 2.5 kilometers. Okay, now coming back here, so now this is the modulating frequency modulator, okay, which controls the frequency of the RF amplifier VCO, right, and that is so this is the modulating frequency 5 to 300 hertz. This is the main VCO which generates the RF signal, right? So from this center frequency, this will be going plus or minus 300 or plus or minus 100, whatever we set here. Now this is there is a power amplifier through a coupler. And it is being transmitted, because a portion of what is being transmitted we need to give it to the mixer also, because once we receive the signal, again you will have a receiver antenna. Okay, so these are the antennas which are fixed on the bottom surface of the aircraft, right? These antennas, if go back here, right here you will have a transmitting antenna and the receiving antenna on the bottom fuselage. Okay, so this is what on the bottom fuselages you have a transmitting antenna and a receiving antenna, and then you have a mixer. So what the mixer does is it compares the present transmitting frequency with the one which is received. So these two signals, okay, what is what has been transmitted, okay, that goes and comes back. By that time this has changed already, right? So then you get a beat frequency, right? So what this mixer is done, it's do comparison of these two signals out here. Okay, that is what this mixer does. So they are comparing these two, so it will generate the beat frequency, right? Then you pass through a low pass filter, a limiting amplifier, and that frequency will be can be put into a frequency counter, and you need to have some calibration mechanism. So an indication proportional to that frequency, okay, that beat frequency we saw is proportional to the altitude, so that can be displayed as an altitude in the cockpit, right? So this is one way of implementing it. The second way is say small modification. Again, you have a modulator, VCO, power amplifier, and transmitting antenna, receiving antenna, mixer. You have VCO. So this VCOs are different. Okay, this VCO is in the RF domain, right? This VCO will be in the beat frequency domain. Okay. So now initially you have your expected beat frequency somewhere in between. You would have tuned the VCO. So now it will compare these two, this beat frequency with the frequency which is being given by the VCO, and if it is difference, if there is a difference in this frequency and phase, so you have a phase frequency discriminator which will tune the VCO to this particular frequency. Okay, and now finally this VCO and this beat frequency they will be the same. Okay, so it's a closed loop system. So you have a phase frequency discriminator, the output of which is tuning the VCO. Okay, so ultimately what we are achieving is we are making the VCO to oscillate at the same beat frequency which we are receiving. Okay, so this is a closed loop system. So now what happens is finally the tuning voltage which is being generated in this system will be proportional to the height, right? Beat frequency is proportional to the height, right? Proportional to the height in this case, because I am talking about radio altimeter, it is the radio height or the range. So this range, okay, the beat frequency is proportional to the range, and beat frequency is equal to the VCO frequency, and the VCO frequency is proportional to the DC tuning voltage which is being given here. So I can say the DC tuning voltage will be proportional to the height of the aircraft with respect to the ground or the range of the radio altimeter. Okay, so and hence that can be amplified and given to a radio altimeter. Okay, so with this we come to an end of this particular lecture, and in the next class we are going to talk about unmodulated CW radar, and subsequently we will talk about MTI and Doppler radar. Thanks a lot.